So welcome back from our little break. So so again, as I mentioned, I don't remember when, last week, then we're only going to officially cover 9.1 and 9.2. So the quiz on that is due a week from today, which is on the 8th. And that's quiz 10, I believe. Now, quizzes 11 and 12 are extra credit. No, you got to learn something on your own. So they are over 9.3, 9.4, 9.5, and probably 9.7. I don't think there is 9.6 on that. And the last, I think those are available until Friday. Yeah. So after you're done with the final, you can still go back and play with that if you want. Okay? All right. Well, these two sections, I'll be covering them simultaneously. They're dealing with solving systems of equations. So chapter 9 is all about systems of equations and different ways of solving them. So 9.1 will focus on system of two linear equations with two unknowns. So two variables. And 9.2 will be dealing with three equations, three variables. Okay? So I'll be really covering them both at the same time. You know, the techniques are very similar. So we're just going to spend this whole week covering that. So I'm just going to give you an example of a system of equations with two unknowns. So something simple like this. X minus y equals 5 and 2x plus y equals 1. So, well, there are a few techniques that we can do. You just describe something that we call substitution when we solve for one variable and we substitute into the other equation and so forth. There's another technique called elimination when we kill variables as we go along. And it's really, when you go past 2 by 2 case, that's what I'm going to be referring to, 2 by 2, two equations, two unknowns, into anything higher than 2 by 2, substitution won't work. I mean, your substitution gets really messy. But in essence, what we're looking at, if I just ask you to look at each equation individually, the first equation is just equation of a line, right? I mean, we can graph that line really fast. X minus y equals 5, so what does that mean? Y equals x minus 5, right, if I solve for y, right? So how do you graph that? Y-intercept is negative 5, the slope is 1, right? So that's that first equation. Now the second equation, 2x plus y equals 1, so if I solve for y, y equals negative 2x plus 1, right? I can graph that really fast. The y-intercept is 1, and the slope is negative 2, so something like that. So we're really looking for this point. this would be the solution let's see, to the system. Okay? So we're looking for the point where two lines intersect. Now, of course, we cannot do it graphically. I mean, we can if we graph very, very carefully. But if our solution come out with fractions and things like that, it gets pretty tricky. So there are really three things that can happen. You can have two lines that intersect at one point, so you get one pretty solution. Or you can get two lines that do not intersect, two parallel lines, right? So that will mean no solutions if the lines are parallel. Or you can get that one line overlaps the second line perfectly, so they'll have infinitely many solutions. So again, three things can happen. One solution, no solution, infinitely many solutions. Is that okay? All right, so two techniques that we're going to focus on when dealing with equations with two variables. So first technique is called substitution. So this is where we solve for one variable in terms of another. And then substitute into the second equation. Huh, nobody's online. So again, my system is x minus y equals 5 and 2x plus y equals 1. So it really doesn't matter which variable you solve for in what equation. You can flip a coin. Well, you're going to need four-sided coin, right? Because you have four options. You can solve for x in the first. You can solve for y in the first. You can solve for x in the second. You can solve for y in the second. Doesn't matter. Whichever you feel is easier, then go for that one. So which variable in what equation would you like to solve for? For what? X. All right. Again, doesn't matter. There's no wrong answer to that question. There might be slightly better options. So yeah, x is perfectly fine. So if I solve for x in the first equation, it is y plus 5, right? So then I'm going to take that value, that x, and I will replace the x in the second equation with that. So x equals y plus 5, so I'm going to replace x in the second equation with y plus 5. So if I do that, I'll get 2 times y plus 5 plus y equals 1. Right? Which becomes a linear equation with one variable. It's really easy to solve. So distribute 2y plus 10 plus y equals 1. And then just solve for y, which is very trivial. Right? So it's 3y equals negative 9. Divide both sides by 3. Y equals negative 3. Is that okay?
So y equals negative 3x, when you plug that back in again?
Yeah, so you can take that value, go back in here, y equals negative 3, so it'll give you the x, right? X equals y plus 5, but y equals negative 3 now, so x equals 2. So the solution is really an ordered pair 2, negative 3, because we just found a point on the plane. X equals 2, y equals negative 3. From the graph, it was kind of looks like 2, negative 3, doesn't it? And it was a very sloppy graph, but sure. What's your point?
It just gets there a lot of time.
I'm still not following what your point is exactly. Ah. Anyways, is that okay? Good. So this is substitution. Another technique to solve equations called elimination. How many L's do you need in elimination? Just one? Yeah, one. That's where you get to kill a variable. So again, if I go back to the same system, x minus y equals 5, was it? And 2x plus y equals 1, is that right? Yeah. Well, just like with any equation, there are a few legal moves that we can do. We can always multiply both sides of an equation by a non-zero quantity. Right? If I multiply one side by -5, I have to multiply the other side by -5. That's perfectly legal. And we can always add the same quantity to both sides of the equation. Right? Just like with any other equations, we can always operate with that. So now, so that means I can add two equations together because they're equal, right? This equal sign means that 2x plus y equals 1, right? So if I add 2x plus 1 to the one side and I add 1 to the other side, it will not affect the balance because they're equal, right? So I can actually add the two equations. That's perfectly legal according to this rule. I'm adding the same quantity to both sides. But see what happens. If I add the two equations, what will happen with the y values? Yeah, you have a negative y and a positive y. So if you have a variable that have opposite signs, and I mean same coefficient with opposite signs, they will cancel. So if I actually add the two equations as they're written, see what I get. 3x equals 6. Because y is canceled. Now I can solve for x, can I? I can divide both sides by 3. X equals 2. Yeah. So x equals 2, you can now plug it back into any one of these two equations. Doesn't matter which one. Let's say the first one. If you take x equals 2 and plug it in the first equation, it is 2 minus y equals 5. Solving for y will result y equals -3. So you still have a solution to -3. Does that make sense? Not necessarily. I mean, let me give you this example. 4x plus 3y equals 11. Negative 5x plus 2y equals 15. So I want to solve this system. Again, I can use substitution, I can use elimination. Substitution will get you very upset very fast. Yeah, negative 5x. Because if I ask you solve this by substitution, no matter which variable you choose to solve for, it's kind of going to suck, right? I I mean, if you choose x, you have to subtract 3. If you choose x in the first equation, you'll have to subtract 3y, then divide by 4 will create fractions. Then you have to substitute that fraction in this x, multiply it by 5, -5. We'll get messy. Okay? It's doable, but it's messy. Now, at the same time, if I try to do the elimination, all coefficients are different, right? But remember, I can multiply both sides of an equation by whatever I like. So I can actually multiply each of those equations to balance the coefficients. So pick a variable that you would like to kill, x or y. Again, it doesn't matter. Sometimes it's easier than the other in this case. You want to kill y? Sure. So you see the coefficients 3 and 2, right?
You multiply like the entire top one by 2.
Uh-huh. So 3 and 2, if those were denominators, what's the least common denominator for 3 and 2? 6, right? So I can multiply the first equation by 2 to get 6. Now, I want to get -6 in the second equation, so they cancel. So what should you multiply the second equation by? -3. So if we do that, the first equation now becomes 8x plus 6y equals 22, while the second equation is positive 15x minus 6y equals -45. Right? If I do it like that. So now if I add two equations, the y's cancel. And again, we could have killed x first. That part doesn't matter. So what happens? You add 23x, y's cancel, equal, -23. Isn't that pretty? So what is x then? X is -1. Is that okay? I can now take -1, substitute into any one of these equations and solve for y. Or I can do the same thing and kill x and solve for y. Because sometimes if your answer comes out very fractional and very ugly, sometimes it's hard to plug it back in. So you can do elimination again on the other variable. Does that make sense? -1 is easy to plug in, right? Which equation would you like me to substitute -1 in? First or second? Sure. Again, doesn't matter. So -1 goes into the, let's say, substituting in the first equation, will give you 4 times -1 plus 3y equals 11. So it's -4 plus 3y equals 11. Add 4 to both sides. So 3y equals 15. So y equals 5. Does that make sense? Let me show you this on the side here. So what are my two equations? 4x plus 3y equals 11, and -5x plus 2y equals 15. Let's say I don't feel like plugging -1 for x. I can do elimination again and solve for y this way. So if I kill x, I would have to multiply the first equation by 5 and the second equation by 4. Do you agree with that? So they get the same coefficient opposite signs. So I'll end up with 20x plus 15y equals 55, and -20x plus 8y, is that right? Equals 60. Right? So if I add them, I'll end up with 23y equals 115, divide by 23, y equals 5. So it's the same solution. Right? And again, you want to do it this way if, let's say, x was not -1, but, 12/17 or something like that. So you don't feel like plugging that back in. Does that make sense? Let's try another one with the substitution. Okay. So if I want to solve this by, did I say substitution? I meant elimination. I want to do elimination. So we want to do elimination here. Which variable would you like to kill? Doesn't matter. Whichever you hate the most. Why? Really? Okay. So how do you get y's to go away? So you have -3 and +6. Just multiply the top by 2. The bottom one is happy. Right? So if I do that, we'll get 2x minus 6y equals 2. And then -2x plus 6y equals 5. Right? What happens? Yeah, x's cancel and y's cancel, and we end up with a 0 on the left. On the right, we end up with a 7. Right? So what does that mean? Right. No solutions. You can never make that work. Right? So that basically means you have two parallel lines. You have two lines that have the same slope, different y-intercept, so they don't meet. So this right away means no solutions. That's impossible. Okay? So two parallel lines. Yeah, if you get something like that, 0 equals 0 or 7 equals 7, which probably never going to happen, but if you get an identity that needs no extra work, then it's all real numbers. So, yeah. Well, actually, I'm sorry, take it back. Not all real numbers, but any point on the line will solve that equation. It's not just any point. It's just any point along a line that's overlapped. Okay. Good. Well, let's try. This is weird. It's very weird. My printer is not good. Printed the same thing twice. I don't know, it has a brain on its own. Okay, so how is that? All right. Want to try a 3x3 case? No? Yes? Okay, let's try a 3x3 case. Now, so since my printer didn't print my examples of 3x3 cases, we're going to have to make some up. So I'm not promising pretty answers, but so let's just make up an example. So we have three variables, x, y, and z. So let's say we have, let's start something simple. X plus y minus z equals, I don't know, 6. And then -2x plus 3y minus 2z equals -1. And then 3x, oh boy, this is going to be awful, minus 4y plus z equals 1. Okay. So this is a system of 3 equations and 3 unknowns. Now, to do this graphically, it won't be a pretty thing to try to do this graphically. We don't know this yet, but let's say a graph of each one of these equations is a plane. Okay, so you have a plane somewhere in space. It's no longer a line on the set of axes, it's a plane in the space. Okay, so you have a one plane, another plane, and another plane. Hopefully they'll all meet at one single point. Well, not necessarily a cube, but they just, you know, like you have 3 pieces of paper, just kind of, hopefully, you know. No, they can meet at one point. So if I have another plane like that, I'm not good at drawing planes, so let's say they met here. And then I have another plane going like this, so they'll kind of meet at one point. But you can have, you know, planes like, you know, one plane like this, another plane like that, another plane like that. So there's no point that they have in common, right? You know, these two planes meet on the line, these two planes meet on the line, these two planes meet on the line. But there's no point where all three of them meet, right? You can have three planes like this, like pages in your book, they'll meet along the same line, so that might have infinitely many solutions. You can have two parallel planes, no solutions there. Or you can have three planes overlapping perfectly. Then each point on that plane will solve it. So there are options there. And it's very hard to visualize, and your calculator won't be able to do any of that. Okay? But we can solve this still. Okay? By kind of following this elimination idea. And we owe part of this theory to good old Gauss. I think we might have dropped his name in this class. Gauss. So what we're going to do now is called Gaussian elimination. So we're going to manipulate this system till it looks like this. You have an equation, ax plus by plus dz. Oh, let me try it again. It's messy. So you have an equation that has all three variables. Then the second equation has only two variables. And the third equation has only one variable. I don't know. Jz equals k. I lost track of the alphabet at some point. Okay? So what we call this a triangular system now. You have all three variables in the first equation, just two variables in the second, only one in the third. You see how we're going to solve that? Because if you have this third equation, you can solve for z really fast, right? Just looking at the third equation, it's just a constant times the variable equals a constant. We can solve for z. Do you agree with that? In the third equation? So if I know z, I can plug it into the second equation and solve for y. And now I know z and y, I can plug them in the first equation and solve for x. That doesn't matter, whatever you like. That's not the same. So I mean, it could be the same. I'm just saying, just constant. So our first thing that we're going to do, we're going to try to turn this into a triangular system. So first, we're going to kill x's in the equations, in the second and third equation, and then kill a y in the third equation. I want to get rid of this part right here. Okay. Now, also keep in mind that it's okay to interchange the equations in the system. That, if this one is the first equation, doesn't mean it's always going to be the first equation. I can just interchange two equations. It doesn't affect the system. Does that make sense? I mean, it doesn't. That's just completely random that I wrote them in this fashion. Okay. So, but we're going to be killing those variables by the means of elimination, as we studied before. So, for example, I'm going to kill negative 2x, right? So it feels like if I multiply the first equation by 2, and I add it to the second equation, the x's will go away, right? So this is what I'm going to do. I'm going to say, okay, so equation, let me write it like this, equation 2 plus 2 times equation 1. That's what I'm going to do. I'm going to add the second equation with a double of the first equation. So what we're going to have is, so let me copy the first equation, x plus y minus z equals 6. And now let's do this in our heads. 2x plus negative 2x is what? Remember, I'm multiplying the first one by 2. What is that going to give me? So x's are gone. Then 2y plus 3y gives me what? Remember, I'm multiplying the first one by 2. So 2y plus 3y is what? 5y. So actually we're going to have 5y Then negative 2z minus 2z is what? Negative 4z. And then 6 times 2 is 12. Negative 1 is 11. So this is where this came from right here. I multiplied the first equation by 2 and added it to the second equation. So that got rid of the x. Is that okay?
Does that take place with one of those?
Yeah, so I just replaced the second equation with that new one. I kept the first one.
Not fixing the first one.
Well, because I didn't feel like doing it. I could have replaced the first one, but it was easy to operate with the first one because the first one just has x. So it's really easy to use that one to kill the other ones. You just multiply first by 2, you kill that. You multiply first by negative 3, you kill that.
Well, how do you know you're killing that one and not the other one?
What, the third one?
No, the top one. Like,
Again, it's just,
it'd be the same.
yeah, I can, again, you can choose any equation. You, as I said earlier, you can just rearrange them in any order you like. It's just easier to use that single x to kill the other constants because you just multiply x by 2 and x by 3, right? But you could have rearranged them any way you like. It doesn't matter. So there is no real, precise way of doing that.
Like, if you were to try this,
Yeah.
how do you, like, how do you know which ones you pick, like, the other two? Like, because you killed, I mean, you killed both of them.
Well, yeah, I'm about to kill the third one, right? But that's what I'm gonna do. I'm killing these two terms, and I'm using the first one to kill those two. I could have rearranged that any way you like. It's just in this case it's a little easier, and this was makes it confusing because there is no wrong way of doing that. There is an easier way and there is a harder way, but there is no wrong way. It doesn't matter which equation, in which equation you're gonna keep the x. It doesn't matter. Okay? I could have rearranged it. I could have put this equation all the way on the top. I can rearrange it like that. Well, then I don't know what you're asking. Yeah? Do you understand what I'm doing?
So, 5y minus 4z what is not equation 2?
It is a new equation too.
Why can't it be a new equation 1?
Because equation 1 should have an x.
But, like, if it was equation 1 and then you could use negative 2x plus 3y.
Like I can?
You can. So it doesn't matter.
Yeah. All it is, this is just a new equation that's combination of some other equation. Okay? Now, let's just focus on killing that 3x. How would we kill 3x? How would you kill this 3x? Yeah, you would just multiply. So you go equation 3 plus, negative 3 times equation 1. That's kind of the way we do that. So if we do it that way, let me take it on the side here.
First one is not equation 1 times 2.
All right. So if I multiply the first one by negative 3, I'll get negative 3x minus 3y plus 3z equals negative 18. And the original third equation was 3x minus 4y plus z equals 1. Right? So if I add them, I'll end up with negative 7y plus 4z equals negative 17. Right? If I kill that x in the third equation, that's what I'll end up with. This is actually working out better than I thought. But But does that make sense what we're trying to do? Now, again, let's focus on this logic here. The logic is to get, and again, it's written in this way. I mean, if I rearrange the equation like that, if I flip the order in which way I write x, y's, and z's, that doesn't matter either. But the goal is to get one equation with just one variable, right? Doesn't have to be z, just have to be one variable. Because look what happens here. Is there a variable that's really easily goes away in the last two equations? Z, right? If I just add these two equations, and I'm kind of breaking, I mean, I'm not breaking the rules, but I'm not going exactly to the letter here, because at some points you just have to start getting creative. Because you can solve for y really fast. Do you agree with that? Because if you just add these two equations together, what do you get? Yeah, negative 2y equals, well, negative 6, right? It's 11. Yeah, that's all right. So then I can solve for y, can I? So what is y? 3. So now you can use that to substitute back, right? If y equals 3, let's say if I plug it into this third equation, negative 7 times 3 plus 4z equals negative 17. So what is this? Negative 21 plus 4z equals negative. Right, I didn't. Because really, I used the top equation to reduce my two lower equations into 2 by 2 case. Then I'm really now solving 2 by 2 case. Well, I'll use the top one to go back and solve for x. Because I'm using the bottom two to find y and z. And when I know y and z, I can find x. Right? Because look, it's negative 21 plus 4z equals negative 17. So add 21 to both parts. So it's 4z equals 4. So z equals 1. So we didn't really put it into that elimination form, but we can still solve it. Because again, the idea is when you get this thing right here, that's easy, always easy to solve, the 2 by 2 case. You can use elimination, you can use substitution. When you get those two variables, we got z, we got y, I can go back and find x, right? Because now x would be x plus 3 minus z, which is 1, equals 6. So x plus 2 equals 6. So x equals 4. Oh, this has come out really pretty. Didn't expect that. I know. I'm probably a genius. Just build a system that has such pretty solution. So the solution now is an ordered triplet. It's x, y, z. You have to put your variables in order. So it's 4, 3, 1. That's the solution. Well, I mean, it gets messier. But I mean, again, if we just get this idea that we want to kill one of the variables entirely, and again, it doesn't matter which one. I mean, we don't have to follow this idea to the T. Is if you can turn, if you out of those three equations, you get a little system, 2 by 2, and you solve that system, and then you go back and find the third variable. Okay? So, well, let's just randomly make one up. Sure. Toss some numbers at me. 4. Good. How about, I'll do the next one. How about negative 2x, don't have a y, minus 3z equals 1. Is that okay? I mean, we don't have to have all the variables. It's just... Yeah, you still have three variables, right? You still have x, y, and z. The first one has a y, so it still has three variables. But the point is, if I don't give you another equation, you won't be able to solve this system. You need another equation to solve this system, okay? So we can make one up again. Anything you like. Would you like? Come on, it's just. All right. Okay? Because look, what I see right now is that my second equation is missing a y, right? So if I, let's say, turn my third equation, if I get rid of the y in my third equation, then I'll have two equations with just x and z's, right? If I kill this, can I kill this by using the first equation? How would you kill this y by using that negative 2y? Yeah, you'll just go multiply equation 1 times 2 plus equation 3, right? Because if I do that, what do I get? So 3x minus 2y plus z equals 4. Then I have negative 2x minus 3z equals 1. So if I multiply the first equation by 2, and I add it to the third equation, so 3 times 2 is 6 plus 6 looks like 12x. Then negative 2y times 2 is negative 4y plus 4y. That's gone, right? Then z times 2, negative z gives you just 1z, positive z. And then 4 times 2 is 8, plus 7 is 15. What? Well, you don't have to. It's just a polite thing to do. Just kind of keep track. Because I just changed my system into that. It's the same system. But look, my bottom two equations is just two equations, two unknowns, right? If I just write them on the side, it's really negative 2x minus 3z equals 1, and then it's 12x plus z equals 15. Forget about everything else, just solve this system for x and z. Can that be done? How would you do that? Again, you can use elimination again. If I multiply, let's say, the first one by 6, right? If I multiply the first one by 6, I get negative 12x minus 18z equals 6, and then 12x plus z equals 15. I add them. What do I get? Negative 11z equals 21, right? So z equals negative 21 over 11. The bottom by 4. Yeah, by 2, yeah. You just have to do like you would do with the common denominators. Just multiply. Did I make a mistake? Oh, because my z's looks like 7. So that should be 17z in here, right? So that's wrong. Yeah, it's negative 17, right? It's negative 18 plus 1, so negative 17z equals 21. So z is negative 21 over 17. Is that better? Did you have this part? So anyways, you found z. Now you can go back and find x. Now things about to get really messy. But to find x, you just plug z into any one of these two equations. So it's, I don't know, let's do the third one. So 12x plus z, so it's minus 21/17 equals 15. Right? That's a linear, ugly linear equation, right? We can solve that one for x. Can we? How would we solve that for x? Yeah. Yeah. All right. So 12x is 15 plus 21 over 17. So what is 15 times 17? Anyone? 255? No? Yes? So 12x equals 276 over 17. So divide by 12. X equals 276 over 17 times 12. I can reduce that by at least a 2. So 138. I can reduce this by 4, actually. 17 times 6 reduced by 2 again. 69, is it? Over 17 times 3. Wow, I can reduce this again. So 12 goes into 276. That's nice. Twenty-three seventeens. Is that right? Of course, you have better ways to reduce fractions. It's just reducing a fraction. Okay? So we got z, we got x. Well, now we can go back and find y. Again, you can plug it into any equation you like. Let's go for the first one. So it is 3 times 23 seventeens minus 2y minus 21 seventeens. That was z equals 4. Right? Well, that's kind of awful, but hey. So what is this? This is 69 seventeens minus 21 seventeens minus 2y equals, why did I say negative 4? Was that negative 4? Just a 4. Equals 4. So 58, no, 48. 48 seventeens minus 2y equals 4. So just solve for y. Pretty ugly. But anyways, right? I mean, I can divide everything by 2 right away to make it 24 17 minus y equals 2. So this way it's 24 over 17 minus 2 equals y. So y is 17, 24 minus 34. So y equals negative 10 seventeens. I think. I don't know. It's really messy. So the solution came out to 21 seventeens, negative 10 seventeens, and what was z? Negative 21? No, 23 here, and 21 there. So does that make sense, what we're doing, the ideas? Because what makes this thing hard is that you have options. There's no right way of doing these problems. It's just don't break those 2 rules. You know, if you multiply one side, you multiply the other side, and you can add any 2 equations. So just kind of, you know, It's all about reducing your system to something smaller. It's much easier to do this with matrices. That's what the rest of the chapter 9 will actually introduce the notion of a matrix. These problems become much easier. You can, if we gotten through the entire chapter 9, we would learn some really neat and fast techniques of solving these types of problems. But for now, we just have to be a little miserable with this. How's that? Okay. So there are some word problems we should try and do. Now my printer didn't do them. Let's do a little break while I fix that. We'll do a few word problems. So I want to do a few of these word problems. I'm actually going to work backwards here. So first is a classic example of mixture problems. By the way, we've done word problems that kind of involve two equations, two unknowns. We just never really thought of it that way. But now we can. So here's a mixture problem. Read the story, see if that makes sense. Does the story make sense? You have two types of coffee, priced differently. You mix them together to get 10 pounds, priced at that. Okay? We want to figure out how many pounds of each brand to mix. So first, let's throw in some variables. How many variables are you going to have? 3? What's the third one? Well, the 840 is not a variable. But 2 variables, right? So what do you want to, again, it can be f and k just to make it easy, right? Doesn't have to be x and y. You can just go with f for French and k for that other one. So f pounds of French roast, and k would be pounds of Kenyan coffee. All right, f and k. So let's build some equations. Well, but f is already in pounds and k is already in pounds. So if we just add them, that should equal to 10, yes. Right? Okay. 9f plus 7.5k. I don't know. Well, not 840, 10 times that, because this is $9. F is already how many, because we're not averaging them yet. So that's the total amount, right? The total. Now the total will be 84, right? It's 840, 10 pounds to that, right? So these are our two equations. F plus K equals 10, and then 9F plus 7.5K equals 84. So it's the rate times the amount. Rate times the amount equals rate times the amount. Well, that's a simple system, isn't it? It's a 2 by 2. You can solve it any way you like it. How would you like to solve it? Elimination, substitution. Elimination, which you want to kill? F. You can do substitution, doesn't have to be elimination. So multiply top by -9, is that right? -9f minus 9k equals -90. 9f plus 7.5k equals 84. Add the 2 to get -1.5, is that right? K equals -16. By 16, 6, of course. 6. So what is K? Which is? What? How can you not know? What is 60 divided by 15? 4. All right, 4. So K equals 4, so therefore, what is F? 6. You have 4 pounds of that Kenyan coffee and 6 pounds of French. So this will end up costing $8.40 per pound. So if you mix it in that fashion. Okay, so if you mix 6 pounds of French roast with 4 pounds of Kenyan coffee, you're going to end up with 10 pounds of a mix that is worth $8.40. Right. If I didn't know the total, well, just yeah, make that one up. That didn't matter. Just if it's 1 pound, then F plus K equals 1, and this equals 8.4. It will give you the same solution. Yeah. So yeah, 10 is really a made-up number. Could have been 100, would still have the same solution. Is that okay? So that's a good question. All right. An airplane flies a 3,000-mile distance from Los Angeles to New York with a tailwind in 5 hours and return against the wind 6 hours. Find the speed of the airplane and the speed of the wind. Right? So that should be interesting. Well, depending on what is X, what is Y. Well, what are the variables here? I mean, I know where Los Angeles is. I know where New York is. Time is given 5 hours, 6 hours. The speed. I don't know the speed of the plane, and I don't know the speed of the wind. That's what we need to find. We need to find the speed of the plane and the speed of the wind. Right? So any way you want to label it, again, if you want to go with X and Y, so let's say X is the speed of the plane, and Y, what? All right, A and W. Let's do A, W for airplane speed of the wind. And again, that's the beauty of it. You can label them any way you like it. You can put a smiley face and some other one of them. What do you call them? What? You can do frowny face. What? Yes. We'll have another math faculty. He invented one. I'm not going to tell you what it is. I mean, I'll draw it. He claims that that was his invention. It seems too obvious. It's not, but it can be. I don't know. Maybe you know this. It's like that. That's what it is. Isn't that cute? So, anyways, let's get back to solving this problem.
Say what I have.
I could do my best because I haven't solved it yet, but what do you have?
Well, I mean, like,
Okay, go ahead.
5a plus w equals 3,505.
No. Say it again. Is it, because you see, if it's 5 times a plus w equals, oh, okay, because you said 5a plus w, I hear this as 5a plus w. But do you have it like that?
Should
I don't know. Because
Yeah.
if you go with the wind, then your speed is whatever the speed of the airplane plus the speed of the wind. The wind helps you. Hang on a second, right? That's the speed going with the wind. What is the speed going against the wind? A minus W, right? So this is the speed with wind, and this is speed against. Now we also know that distance equals rate times time, or rate equals distance over time, or time equals distance over rate. So you can do exactly what you said. If I take the speed with the wind, A plus W, and I times it by 5, I'll get the distance of 3,000, which is equivalent, this is really what you want to have, is A plus W equals 600, right? Well, if you divide by 5. I'm really focusing on this formula. Rate equals distance over time. So if it's 3,000 miles in 5 hours, then your average speed is 600 miles per hour. Well, the other one, A minus W, is the same as 3,000 over 6, because it took 6 hours. So it's A minus W equals 500. So the speed with the wind was 6 miles an hour. The speed against the wind was, 600 miles per hour with the wind, 500 miles against the wind. Now we can solve this very easily, right? How would we solve that? I mean, elimination kind of stares at you there, doesn't it? If you just add two equations, you'll get 2a equals 1100. So a is 550. So that's the speed of the plane. No, it's just elimination. If you add the two, y just cancels, right? It's really simple. So if a is 550, what is w? But just focus on the equations. If a is 550, so w has to be 50, right? And just look at any one of those equations, plug it in. W equals 50 miles an hour. Right? So good. You had the right idea. You just, parentheses were important there. But yeah, we're just operating with the formula distance equals rate times time. You can just manipulate it any way you like. Is that okay?
So the airplane is going 550 miles an hour?
Yeah, 50. So if you're going with the wind, so you're going 600. If you're going against, it's slowing you down. We can change everything, make an airplane into a boat and wind to the current and jump in the river. Kind of the same thing, with the current, against the current. I don't know if we're ready for that one. What? Okay, sounds like we should do it now. 1 8-ounce serving. Yeah, I'm not following that. The
Well,
the
to the beginning, and then it's live.
the wording kind of confuses me. 1 8-ounce serving each of. What does that mean?
Oh, what?
That first sentence. If it makes sense to me, if you decipher this, I think I'm lacking my.
So, a thing of brewed coffee and Red Bull
Total
and
of
Mountain Dew,
one.
they're all 8 ounces.
So you have 8 ounces of one, 8 ounces of another, 8 ounces of another, total 187.
And then the Mountain Dew only contains 197. So you only know how much caffeine Mountain Dew has.
No, I don't think so. I think it's all three together. But it's like, am I talking about 8 ounces of mixture or 24 ounces total? What does this each of thing means? I don't get that.
Like,
I think it's one
each
each.
one is 8 ounces.
So I have a glass of coffee, 8 ounces, glass of dew, 8 ounces, and Red Bull, 8 ounces. Total 197. So yeah, this is each of. I'm upset now. No, you should like. This is your language. I'm just making stuff up. I don't know what this. Never made sense to me. I just.
So 8 times each of those variables.
Well, if it's a three-variable problem, it's probably one of these.
8 plus 8 off.
I know this is what's confusing me. That each off. What does that mean? I've never heard each off.
Yeah.
Of brewed coffee, Red Bull, and Mountain Dew.
Or maybe like a semicolon in there, just something. Put some kind of a. Yeah, but it's. I agree. Should put one of those in there. So anyway, so let's just do variables. Let's do coffee, Red Bull, and the Mountain Dew, right? Each represents one serving. Okay. Now, happen to be 8-ounce serving. I don't think that's relevant. It's just a serving. Now, together, that's how I understand this. If you put the three servings together, you get 197 milligrams of coffee. Okay, so this is the caffeine amount of caffeine in each serving. Okay, so C would be the amount of coffee in the serving of coffee. R is the amount of coffee in the serving of Red Bull. M is the amount of caffeine in the serving of Mountain Dew. If you add them all together, 197. That's how I understood that problem. Do you agree with that? So we deciphered the first sentence. That's the first sentence. If you add the caffeine in all three servings, 197. Now, let's decipher the second sentence. We'll deal with that one later. It's the third sentence. One serving of brewed coffee has 6 milligrams more than 2 servings of Mountain Dew, right? Okay, so we're about to start comparing 2 servings of Mountain Dew with the 1 serving of coffee. Actually, I'm going to split them like that. I'm going to put, they're not equal yet. They're not equal yet. C plus 6? Oh, 2M plus 6. Which one is bigger? Is the amount of caffeine in coffee or in Mountain Dew? Which one is bigger?
Yeah, 6 more
In
in coffee than 2 servings.
All right, so caffeine by itself contains more caffeine than 2 servings of Mountain Dew. So then I should be adding 6 to this side to balance it out. Because 2M is already smaller than C, so I need to balance it out, right? Well, right? It's like, okay, caffeine has 16 milligrams and Mountain Dew has 5. 2 servings of Mountain Dew is 10, right? Still, 16 and 6 greater than 10. How do you balance 16 and 10? You add 6 to 10. Or you subtract 6 from C. Okay, let's decipher the third one. one serving of Red Bull contains 37 milligram less caffeine than one. Oh, each off again. Okay, okay. What does that mean? So they're each off means, put together those, right? That's okay. So that's what we assumed in the first one, so we have to stick to this. So one serving of Red Bull contains 37 milligram less caffeine, right? So if I add C plus Mountain Dew on one end and the Red Bull on the other end, Red Bull has 37 less than that. So I have to add 37 to Red Bull to balance them out. Okay, so now let's put them all in one pretty system. So all the variables on one side. C plus R plus M equals 1. I hope this is correct. This is ridiculous. The verbiage was a little off. Minus C plus 2M equals negative 6. Right? If you just kind of less than these two together. That's how we deciphered it. Then C minus R plus M equals 37. Whew. Okay? Well, look, now we just have to solve this thing. Now, remember how we can solve it. The middle equation already is missing a variable, right? So I can do this. I can add these two equations right here to kill R. So that'll give me another equation that's missing an R, right? So right away, I'm going to add equation 1 and equation 3, right? Because look, then it'll just give me negative C plus 2M equals negative 6. I'm just copying the second equation. And then I'll get 2C plus 2M equals, no, 197 plus 37 is 234. Is that right? Okay. So we can solve this system pretty fast, right? Just subtract one from the other. If I subtract, I'll get 3C equals 240. Well, so I'm doing this times negative 1. That's what I'm doing. So that's C, 2C is 3C, positive 6, 334 is 240. Those cancel. So C equals, what, 80? 80 milligrams. So one serving of coffee contains 80 milligrams of coffee, right? Then I can solve for M. So this is negative 80 plus 2M equals negative 6. I'm just using the first equation. Is that okay? So then 2M equals 74. So M equals 37. Right? And then finally we had C plus R plus M was 197. That was the very first equation. So C is 80. Some coming out kind of weird, isn't it? Oh no, not really. Is it weird? It is weird.
As long as Red Bull is less. Yeah, 80.
80, right?
I did the
Yeah, again, there's no correct way of doing this as long as you're doing this. So 88 to 37, does that match that?
You have the answers to the question?
Oh, I have no idea. I don't even know what I pulled that from.
Yeah.
One serving of brewed coffee has 16 or more.
Is one of them,
Yeah, that's true. One serving of Red Bull contains 16 or less.
one is not included in the first
Well, that's true. I mean, the 37s would cancel. This is silly. Where did I get this problem? Let's check the answer. Maybe it's an odd one.
Mm.
21. So we can. So it's section 9.2, 21. So it's all going to be about our interpretation of the each off. But I think we're correct in our interpretation of each off. Oh boy, it's going to take a while. Okay, we're close. So 9.2, question 21. 80, 80, 37. Wow, we're golden. Well done, team, at interpreting the each off. So silly. Okay. Good. I have one more. Money. Let's talk money. All right. How do you say that name? Moira? Is that right?
however you want it.
Yeah, I agree with that. I'm in charge. So she got, I assume that's a she, $15,000 and invested part of it in the money market account, municipal bonds, and mutual fund. Got $730 in interest total. Simple interest, what makes us happy. Otherwise, it gets very hard. And 1 year, it also makes us happy. So the money market pays 4%, bonds 5%, funds 6%. There was 2,000 more invested in the mutual fund. Okay. All right. So let's throw in some variables. Let's just do X, Y, and Z because everything starts with an M. Money market, municipal bond, and mutual fund. They're all M. What? Yeah, let's do that. Let's just do M for market account. M. And then let's do bonds and funds. Right? So this is the amount invested in each. So if you add the three amounts, what do you get? No. 15,000. That's the total that she had. Right? The interest would add up to 730. So the interest of the money market pays 4%, so it's 0.04 times M. Right? It's a simple interest, so it's a rate times the amount times the time. The time is 1, so that makes it very easy. So plus 0.05 in bonds plus 0.06 in funds adds up to 730, right? And then finally, there was 2,000 more invested in mutual funds than in bonds, right? How would you set that one up? The third sentence. So fund is greater than bonds by 2,000, right? So let's just do it fund minus bond, right? Can we do it that way? Is that right? Yeah, okay. Wow, that one is a doozy. Can we solve that one? Hmm? Yeah, I can do it, but let's just have a plan laid out. Because I don't know what we're trying to do, but let me just copy this equation again. the system m plus b plus f equals 15,000. Let me change the one in the middle because that one is ugly, right? Just multiply everything by 100. That's legal. It'll just be a little easier on the eye if I multiply everything by 100, right? Just multiply both sides by 100, make it a little more manageable. And then it's negative b plus f equals 2,000, right? Right. So yeah, looks like if I just eliminate that m in the second equation, then I can get b and f sorted out, right? So let's focus on killing this m, the 4m. How would we do that? Yeah, so it's negative 4 times the first, right? So it's negative 4 times equation 1 plus equation 2. Is that okay? So again, so let's see what happens. Let's just do this in our heads. So 4, that's gone. 4b, 5b, and remember it's negative 4b. So that leaves us with just, I don't know why I did that. So that just leaves us with the b. Negative 4f plus 6f is 2f, right? Equals 4 times 15 is 60, right? Negative plus, so 13,000, right? Now the other one is negative b plus f equals 2,000. Now this one is really easy to solve, isn't it? Right? How would you solve that one? I mean, you already have a b. Yeah, so just add them. So that's 3f equals 15,000. So f is 5,000. Okay. So if f is 5,000, can I find b? It was 73, and that was 60. So what was that? Oh, I think b should be 3,000. Right? Just if you just go in here, if you take 5,000 in here, yeah. So it's negative b plus 5,000 equals 2,000. So b has to be 3,000, right? So if f is 5, b is 3, the total was 15. What is m? What was that? 7,000. So m, because m plus b plus f equals 15,000. That was given. And we found b to be 3,000. Yeah. And f we found to be 5,000. So m is 8,000, 7,000. Yeah. What? So 5, 3, and 7. So usually it's the hardest part is to decipher all the givens and interpret the each ofs, see what they mean. What? In this little set, what if I decide to, don't challenge me on the amount of problems I can throw at you. I mean, I have a whole book in front of me. I can just randomly pick one. But does this make sense, what we were trying to do here? How we do this? And again, unfortunately, we kind of fell behind, so we don't get into matrices, but matrices are fun. It's a lot easier.
So there's like Oxford.
Well, kind of. Well, matrices just focus on coefficients. So the order in which you list the variables really makes. See, I was trying to kind of line up my f's with f's and b's with b's. But if I flip them around, it wouldn't affect the solution because I still have b's attached and f's. I still know which variable is which. With matrices, you drop the variables, you focus on the coefficients. So the order very important. You know, you cannot be just flipping numbers inside the matrix like that. You know, the linear flip is not allowed. But there are some things you can study about the matrix that makes the solution a lot quicker. Anyways, good. So yes, we're done.